Welcome. This is part 13 of the Calc Prep. This is math from the void. Math coming at you out of nowhere. And as much as I would love to introduce this next topic myself, I think I'd rather let Run-DMC do it for us. Be talking about in the next few lessons. We're going to be talking about trig and trigonometric expressions. That's how we'll be spending the next few episodes in the void. So I hope you've studied up on your unit circle knowledge. We're not going to cover the unit circle here. The unit circle is lost in the void. So I hope that you remember it. Now what we're starting with for the first lesson is we're just going to revisit what a sine and a cosine function looks like. We're going to take a look at the shape of the graph. You might remember it has this sort of oscillating or periodic bouncing back and forth, up and down. And we call this a wavelength. It makes kind of a wave shape. What's the general equation for a sine or a cosine function? Let's take a look at this. We have y equals, reduce the thickness on here, y equals a times, we'll use sine for now, of b parentheses x minus c. You might recognize the minus to the x from when we were doing transformations, because when we're doing transformations and when we're writing the equation of something like a circle or a quadratic function in vertex form, the value which is subtracted from the x, this represents some kind of horizontal shift. I'm sort of getting ahead of myself here. Recall this equation. This equation has a certain pattern. What is that pattern? That pattern is as follows. Middle, up, middle, down, middle. This is the general structure of a sine curve. Now, where the sine curve begins on this parent function is simply at 0, 0. But we may have a shift in the x, and we may also have a shift in the y. We may have a reflection, and it will flip over, so the pattern will be flipped. We'll have to take all of these things into consideration when we're looking at the model. But let's just revisit what some of these terms stand for. So the a value. We have the b value. The b value is not a specific feature that we think of on the graph. It sort of is the frequency, but we'll use that b value in a slightly different way than you might think. The c value, as we mentioned, is going to affect the horizontal placement, and this d value is going to be a vertical shift. So we have the amplitude is determined by the a value. The period is determined by the b value. The horizontal shift, I'm going to have to extend this a little bit, is described by the c value, and the vertical shift is described by the d value. I also call this the midline. It'll make sense what that means in a moment. First, let's get a little bit more precise. Technically, the amplitude is the absolute value of a. A could be a negative number, but the amplitude cannot be a negative number, and the amplitude represents the distance from the midline to the extreme point. In the case of the parent function, the standard amplitude is 1. But whatever this a value is will tell us what the amplitude is. The period which is how long it takes before the cycle repeats. The b value is not exactly the period. The period is equal to 2 pi divided by b. So b is actually a horizontal compression factor. You don't need to know that specifically. Now the c value is sometimes called the phase shift, but it means the same thing as the horizontal shift. We just use the phrase phase when we're referring to waves in topics like physics, and so I guess in math it kind of permeated the language. The phase shift, it's basically like the shift to the left or the right. And the c value is the exact amount of the shift. This value for d, the vertical shift, or the midline, is going to tell us the horizontal line where the wave is shifting above and below. This midline might not be at 0. It could be lifted up or it could be raised to a higher y value, and it could be dropped down below the x-axis. So the vertical shift is d units, either up or down, depending on the value of d. If it's positive, it goes up. If it's negative, it goes down. Okay, now that we've paid attention to those things, let's also point out that this represents the maximum and this represents the minimum. So if there's a vertical shift, the maximum and minimum could change, and also if there's an amplitude change, like a equals 5, then we could also have some kind of different maximums and minimums. Let's take a look at the data now. We use these kinds of functions whenever we're talking about things which change or fluctuate periodically. So temperature is a great example because temperature will rise to a similar high value from the previous day, normally, reaching some maximum when it's, what we call summer. So here is a graph with the temperatures in Alaska, probably not very hot in Alaska. We have to identify these features: the amplitude, the period, the horizontal shift, and the vertical shift for this particular model in the graph. So one of the easiest things to detect is the midline, which is the vertical shift, that is the d value. And we can see that it's somewhere right here. It's going to go in the middle of the wave. So this seems to be at about 30, and therefore I would say this seems to be at like 25. So let's say that the value of the vertical shift is 25. I'm sure they're going to have us write an equation. Yeah, they're going to have us write the equation for the model. Now let's find the horizontal shift. Well, I mentioned that sine starts at, let's take a look at it again. Sine starts at the midline. So it normally starts at 0, 0. We want to look at where it hits the midline. So this is a place where we can start it. And that would be, here's February, here's March, here's April. That would be, say, April 10th. So on April 10th, we have to figure out if they're using days or months for the x-axis. They didn't really indicate that. We're going to say that they're using 365 days for one full period, roughly. Yeah, I think that's fair to say, because that's one full year. So the temperature is roughly going to repeat its cycle after a full year. So where is this starting point? Well, we've completed 3 months. This gets a little technical on the calendar, but we have 31 plus, let's just say it's 28 days. We don't know if it's a leap year. Doesn't matter. We don't have to get that technical. And then we have 31 days in March as well, for a total of 90 days plus 10. So like on the 100th day, so we can say that the value for C equals 100. And that means that our model, we're making a choice by doing that. What choice are we making? We're making a commitment. committing to using days as the input variable. Let's call that T. That'll be our T. And the temperature, maybe we'll just call it F for the Fahrenheit. Now, what else do we need to identify? We need to identify the period. Well, we've kind of picked the period. It's 365 days for it to repeat. How can I be certain of that? I mean, there are 365 days in a year, again, unless it's a leap year. And those are roughly at the same spot in the cycle, right? It's like going to repeat after that amount of time. So I think we can say the period here is 365 days, which does equate to 1 year, but we're going to keep it in terms of days. And now let's talk about the amplitude, which is the distance that it is fluctuating up and down. So the distance from the midline of 25. How high does it go, sort of from there? Is it there that it hits it? Maybe it hits it right here, something like that. That seems to go to about 65-ish. If I had to guess, that's not very, very hot for a high temperature of the year in Alaska. And then we have the lowest value, which is going to be like down here. What would you say that is? Let's take a look at the graph. I would say that's like, goodness, that's got to be like almost like -15, pretty much. So that seems to have about the same gap, right? 40? Yeah, 40. That gives us the amplitude. So the fluctuation, or the amplitude, which is pretty much just measuring the amount of fluctuation, is 40 degrees Fahrenheit. Okay, so let's write our equation. Well, if we have 365 days, then what's the b value? That means that 2 pi over b equals 365, which means that b is equal to 2 pi over 365. And that's what we're going to put into the actual equation when we write it out. So we could use y. We can say y is the temperature. Y equals 40 sine of 2 pi over 365. And then we can write t minus 100. And we add the midline, which is plus 25. This will give us an approximation of, what does this measure? It's the mean air temperature. So it's not even necessarily the high temperature of the day, it's the average temperature on that day for that city. So if you wanted to find approximately what the average temperature would be in Fairbanks, Alaska on a given day, you would find out which day of the year it is, which takes a little bit of time, and then you would plug that into this equation, and you would get an approximate value. Okay. Now we're going to use the equation here to approximate the following questions about some temperatures. So now that we have a model, we're going to have to use that model. And it does say assume that the year has 365 days. So it's almost kind of like reminding you that if you didn't already use that into your period, you might want to consider using that. What are the highest and lowest mean daily temperatures? Well, we already found those things by analyzing the function so that we could write the equation, right? So we know that the highest was approximately 65 at the highest, and approximately -15 at the lowest. What is the average of the highest and lowest mean daily temperatures? Why is this average the vertical shift of the function? Well, that kind of makes sense, right? We're going to have the highest points plus the low, and that's how you find the middle. That's how you find the midline. So this is going to be 65 minus the 15, because we're adding a negative 15, and then we're going to divide by 2, which is going to give us 50 divided by 2 for a total of 25 degrees Fahrenheit. And it makes sense that this is the midline, that by averaging them, you're finding the middle of those two values, and so that finds you the midline. Of course, the data probably does not fit the perfect model. As you can see, there's a little bit of a deviation. The blue curve is like a nice sine curve that is best fitting, while the red points, those are probably individual data points for like each day. I don't know if you can see it, but if you zoom in really closely, there are many, many data points. Yeah, it's very dotted. So we have a recording like 30 of these for each month. Okay, so this is a look at the sine equation. Now let's take a quick look at the cosine equation. The cosine equation has a different pattern, so I'm going to write that here. It would be the same format. We would have y equals a with the cosine of b parentheses x minus c, and of course plus the vertical shift d. And the parent function is the same exact shape as the sine curve with the same amplitude and everything like that. It just appears shifted. Rather than starting at the midline, which is where sine begins, cosine begins at the a value. In this case, the parent function has an a value of positive 1. And then we go midline, down, midline, up. Oops, it's kind of bad tracing. It's a little better. And so this is the same as a portion of the sine curve, as you can see. It's just starting at a different place. It's almost as if it were shifted forward. And that gives you the cosine curve. So just keep that in mind when we're looking at cosine graphs and cosine patterns. Now that's our introduction into, or reintroduction, hopefully, if you've seen this information before, reintroduction to trig. What we'll be looking at next is evaluating trigonometric expressions, and this is when things are going to speed up big time. Until then, see ya.